Let's talk about how to make an orbital diagram. In order to do this, you'll want to have watched the videos on the structure of an atom and then the one that talks about shells, subshells, and orbitals. So, in an orbital diagram, we're going to find pretty much a picture of where the electrons are in each of the atom's orbitals. Electrons are going to fill subshells of the atom at low energies first before filling subshells at higher energies. They're going to put one electron in an orbital first before they start pairing up. So everybody at the same energy in a collection of orbitals will have one electron first before any orbital gets two electrons. There are only 2 electrons per orbital, and they need to be of opposite spin. Spin is a quantum mechanics property, which we won't talk about too much here in this video, but except to say that it allows us to distinguish electrons in a particular orbital. Your shell number is going to indicate the energy level of your subshell's orbitals. If you have a lower number, that will tell you that your subshell is closer to the nucleus and thus at a more stable energy. So when you look at the periodic table, there's some helpful information here about shells and subshells. What you want to recognize is that in general, there's one exception, but in general, the row number on the periodic table equals the shell number. The exception to that general rule is found in the D block and also the F block, which is down here. We're going to ignore the F block for right now because we won't talk about too many of those elements, but the D block elements will come up quite often. And what you'll find for the D block elements is that the shell number will equal the row number minus 1. So take, for instance, these elements in the D block. They are in the 6th row, but they have a shell number of 5. So their shell number would equal 5, even though they're in the 5th row. On the other hand, if I was in this region of the periodic table, this is the S block. Remember, S, D, P, and F are all types of subshells. On the periodic table, the columns that we see here give us these different regions of where the subshells are. So the first 2 columns in the periodic table are part of the S block. That middle group of 10 is the D block. The last group of 6 is the P block, the P subshell, and down here in this yellow area we have the F subshell, or the F block of the periodic table. So columns tell us what subshell we're in, while rows tell us what energy level or shell number we're in, with the exception of the Ds. So if I want to build an orbital diagram for an element to talk about where all those electrons are, we need to list all of the orbitals and group them by shell number and subshell type. So I found this image online where someone had already made a orbital, just a generic orbital diagram. What you'll notice here is that we start with the 1s. So, and it is the lowest in energy. Here's my energy axis over here, and so high energy is up here and low energy is down there according to my axis. Now low and high energy can be kind of tricky because it depends on your frame of reference. Are you talking about pulling an electron off, putting it on, just sort of a general energy? I'm not going to get into that too much other than to just say that low in this case is really, we're talking about more stable. So the 1s orbital is considered to be a very stable place for electrons to be because, if you'll recall, that shell number 1 is likely going to contain electrons that are closest to the nucleus. And electrons like the nucleus, so they're pretty happy there. If you'll recall, our rules said that we had to put electrons in orbitals that started low and moved high. So for arsenic, when we look at the periodic table, we see that arsenic has we see that arsenic has 33 electrons. And the orbital diagram, we should be able to put all 33 electrons on this orbital diagram. We're going to represent electrons as half-headed arrows, and either they will point up or they will point down. And the up or down pretty much is going to correlate to one having spin of one direction and the other having quantum spin of a different direction. And you'll recall that we need spins of opposite direction in the same orbital. So now we're just going to think about this as we have 33 electrons and we have boxes to put them in. We know that one orbital can take only 2 electrons. So for the 1s, I've got my orbital right here, and it can take 2 electrons. One with spin up, one with spin down. That takes care of 2 electrons. That orbital is now full. I'm going to go up to the 2s, put another 2 electrons in. That orbital is full. I'm going to go up to the next available orbital, find the 2p, put in 2 electrons in each of those boxes, because this is each an orbital here. The 2p subshell has 3 orbitals of equal energy. At this point, I've used up 10 electrons. I still have ways to go. Put some in the 3s, in the 3p, in the 4s, in the 3d. I'm just filling until I run out of electrons here. And I know that I'm going to stop in the 4p because if we look at arsenic, let me go back here for a minute. If we look at arsenic, it's right here, which is located in the p block. So, and it's in the 4th row, so we know that it should end, our last electron should go into a 4p orbital. And in fact, in arsenic it does. We find we have 3 electrons in the 4p, and you might be curious as to how I know that. Let me go back to my periodic table and point that out. Arsenic here, let me erase some of this stuff so you can see what I'm talking about. Arsenic is 1, 2, 3 boxes in to the 4p subshell. So therefore there are 3 electrons that arsenic has in the 4p subshell. So when I go to my orbital diagram, there should be 3 electrons in the 4p subshell. And the question becomes, do I put them 2 in the first orbital and then 1 in one of the other orbitals, or do I put them 1 in each? If you recall from our first slide, we talked about the fact that electrons will go into an orbital by themselves before they start to pair up. So this configuration, where they are 1 to each orbital, is correct. And that completes my orbital diagram for